So, we continue with our digital printing lectures. So, we learnt till now that inkjet printing is the technology used for printing of textiles, unlike for paper where laser jet also is used. Millions of shades can be produced using this technology. This facilitates the production of photographic images. Continuous inkjet delivery is one of the technologies. Within that continuous, you have several possibilities. This technology generally uses high frequencies because continuously you are supposed to generate drops. So, because the complexity is associated with the continuous inkjet, charging of drops, deflection of drops, ink recirculation because you are putting part of the ink in the drain, and pressurization so that the continuously there is a positive pressure, it keeps on replenishing itself. As I said, operating frequencies of these devices could be at least an order higher in magnitude than those which may be used in drop-on-demand systems. So, we will see some of the things for the inkjet technology like the drop-on-demand. What therefore it means is that you do not continuously keep generating drops, you generate a drop when required. And so, if the design does not require any ink to be used, then there is no drop generated. So, therefore, you do not need to have any drain or any such thing and recirculation of the unused ink. One of the material that is used to excite and the ink surfaces or the bulk, so that the volume within the chamber is changed, let us say by squeezing. A large number of piezoelectric systems may be used for generating drop on demand process. So, piezoelectric material is be one of the transducers. So, historically we have to understand that somebody in the early days noticed that some materials, some crystals, some ceramic materials generate electric charges when temperature is changed. So, they observed change in temperature can generate some charge in some of the materials, and which was interesting enough. So, you begin. So, these are notices, people noticing things happening. Then two brothers, Jack Curie and Pierre Curie, known as the pioneers, they found that the tension or compression can generate voltages of opposite polarity in such materials. So, some polarity if you generate when you pull, and the opposite polarity is generated when you compress. So, that means they saw the potential of such type of materials being used as engineering materials which can drive things. Another scientist, Hankel, termed these kind of effects as piezoelectric effects. That means the crystals, if you deform them in one way or the other, electrical impulse could be done. And it was also seen that you can have the reverse effect, that is, if you pass electricity or subject them to an electrical field, then based on the polarity you can see expansion or contraction of these type of materials. Because the effects are very small, and that is the reason why small things when have to be done, these type of materials will be used. We are looking at some picoliters of drop being generated. That means we are not really looking at a very large deformation. In such cases, only such type of materials can come in handy. If you try to do any other thing which will be always larger, very difficult to control. But so these materials became very important. Other than the crystals, there are people found other materials that are called the ferroelectric materials, which also show and exhibit their in crystalline phases, different phases and domains which can be polarized, and so you can create different structures. The polarization, that means there are some elements within the system which are polarized electrically, and so they have positive, negative, they respond to a positive side or a negative field that is created, and therefore, they also have some properties which are similar properties and exhibit piezoelectric effect. And these type of material today are considered, that is the ferroelectric materials, an important class of engineering materials. Of course, you can use non-ferro materials also. There is a process which is called poling, that is you orient the poles in the piezoelectric crystals. What therefore it means is, like in magnets, you try to work around so that north and south pole elements are oriented, aligned along a direction. Similarly, the dipoles can be, which are randomly oriented, can be polarized, and this process is called poling, so that they are pointing in one direction. If you consider that a crystal or such object is a three-dimensional object, this poling can be done on any direction, x direction, y direction or z direction. This would help people to design systems, how to pass the current and where will they see the result of expansion. So, the behavior of the such type of crystals can be modified by poling. So, you can theoretically pass on a current or apply a field which is parallel to the poling direction. You can apply a field which is perpendicular to the poling direction, and you will see changes in different directions. And that way you would know where to put the material and which direction you want expansion to take place in case you give the field either perpendicular or parallel and so on and so forth. So, it gives you a flexibility in design of any system. So, this is what exactly I said, the dipoles which are randomly oriented to begin with can be polarized in the direction of the applied electric field. Like for example, you have randomly oriented entities they can become polarized if you have, let us say, a field getting created. So, you will have a material which would then be oriented. Now, this orientation, when the field is applied, has one, but what it means is if you apply the field for some time, which is called poling, could be called tuning, that these poles actually almost get oriented in this direction. So, this type of material which has been already poled, where poling has been already done, can be used. Although, when you remove the electric field, some part disturbance can take place, the alignment may shift little bit, but it does not become random. If it does not become random, that means you have a material which would respond to electric fields in a manner which may be desirable at any given point of time. So, some of the examples are like quartz, barium titanate, lead zirconate titanate, which is also known as
PZT.
very interesting material. And the property is that when you change 1 volt, how much dimensional change you may get. You are talking about very small changes, let us say in quartz, picometer, right, which is very small change. But these small changes, so in
PZT.
the change is more than the quartz. So, different materials therefore would have different let us say the D or a piezoelectric constant, and so you will use them according to what you desire. Most of the engineering applications may be using
PZT.
based sensors. So, from the values that we see per unit voltage, that change in dimension is not very significant, is small, right, but we can still exploit it wherever. For example, our drop on demand type of a situation, where we do not require very large displacement of the volumes. Similarly, such type of materials could be used, for example, in transmission electron microscope, where you want to change the or you raise the platform or the stage, you want to raise it by a few nanometers. There is no other way you can raise the platform by a few nanometers other than using some of these materials. And by controlling the electric field, that is the voltage, you can control the displacement, and that is what we would like to see, how the things get used. So, piezoelectric based inkjet printers, which are also drop on demand type. Once we know that this particular sensor is going to displace so much, and accordingly you can design theoretically to begin with. So, the piezoelectric crystals can be used as displacement tool by impressing suitable voltage. So, as a displacement, the displacement could be in any direction, in the x direction, z direction, y direction, depending upon what have we done. The transducer can be maybe attached to a membrane that forms the ink chamber. So, you have ink chamber, so ink chamber has a wall, the wall is made of some membrane which is flexible. And so, on one side, on top, on the side, at the bottom, if you add any such crystal, then after passing the suitable voltage or the applying of suitable field, you will get displacement, and so that much part of volume could be ejected out. Sometimes the sensor itself may act as a wall. So, you can appreciate, as long as the chemistry of ink is not such that this is going to destroy, then you can use that as well, but that is obviously dependent. So, the volume will be proportionally reduced when you apply the electric field, and then ink drop will be ejected. So, it appears that if you control your voltage and you have right kind of circuits, then the drop size can be controlled. Drop on demand, as we said, only means that you are ejecting when you need. So, rest is circuitry, contacts, and a software which communicates. So, some of the things can be simply like what you see here is a piezo device is put on the top. So, either which you call a crystal or a piezoelectric sensor is put on the top of a chamber, which is suitably connected so that you can apply the field. And if this changes the dimension in any manner, becomes larger, then you will have a push and you would get. Sometimes they may only shift and shear either in this direction or in this direction, and that itself will cause some change. That some change is interesting change.
So we can also make them shear.
Yeah, they can shear also. This mode also is called a shear mode. Crystal on top. In this, the electric field is applied perpendicular to the poling direction. So, you have material which has been poled in a direction, and electric field is not applied in the direction of the poling or opposite to that, it is a perpendicular. So, there shears are obtained also. Drop obviously, as I said, generated when needed. No drain is there, so you do not need a drain. So, theoretically it can become a smaller in size. The frequency of the input can be varied, and this frequency will definitely be related to production. And production in inkjet would be considered how many drops have been produced in time, all right. That is the production. We can always say that the production is in terms of how much ink has been consumed, and so the frequency with which it is going to be operating in some way would finally decide what is the production. People can, so they normally would describe the production as how many square meters of the fabric has been printed, rather than what is the speed of the machine. The speed of the machine may change if your area of print is large, and so frequency is one of the parameters which would determine the production also. So, instead of having one chamber, one piezo device, you can have multiple piezo devices which themselves are acting as displacement units, as also may act like chambers. That is, their wall is the part of the chamber itself. The wall is the sensor itself, it could be. They also can act in a shear mode, as if you are just pushing the oil to or pushing the ink to go in forward direction. So, they may receive different inputs at different times. All of them can be simultaneously if the whole area requires the same color, and so you fire all of them. If you feel no less number of drops have to be generated there, so you generate only one or two, you can, that means it has more control. One control obviously is the frequency, other control is the voltage. Now, if it is possible to change all of them, but normally frequency may not be changed very easily, because frequency generation system is a different system. But the software may think of changing voltages. In case that is not there, you can always make sure that some are fired, the others are not fired. So, you can have multiple chambers working side by side, and so on and so forth. So, let us say in this case, let us say this one is not firing. So, it may come, you can control. If both of them fire, then the volume could be different. One of them may fire, the other two do not fire. So, squeezing could be in any of the directions that one can think of. There is a squeeze mode that the whole sensor could be a tubular sensor. There may be a membrane which is holding the ink, but the whole sensor is a tubular sensor, annular, and so the tube will shrink or expand. So, one can have some of these types. So, therefore, once you know that there is a possibility to reduce volume, and interesting is when it comes back when there is a pulse, let us say it is expanded. When the pulse is stopped, obviously it will go back. When it goes back, vacuum will be created, and so there is a ink reservoir from where it will get filled. So, somewhere the ink will keep coming, and so whatever you remove, once it goes back somewhere, because some positive pressure may be there, and ink will just come in. Here the control, as you know, is the viscosity of the ink and the orifice, the diameter of the orifice is such that it by itself cannot fall. So, that viscosity and surface tension will make sure that unless you push, ink will not come. Like in printing, otherwise conventional printing also, unless you put a squeegee, the paste does not move. Here the viscosity is much less compared to the viscosities in their conventional printing. Still, there is viscosity, which is enough, the surface tension viscosity property is enough that the drop will not come out unless pushed. So, there can be the jetting of the ink, sometimes known as, can be by the method that we have talked about above, or methods which could be simple push when the direction of the polling direction and the electric field direction are same. It will be generally a push mode, and you can get the things. Within the DOD, there is another mechanism which people use for generating drops, which is not based on piezo sensor. There are reasons, some people obviously would appreciate those reasons also. Thermal, you may have heard sometime there used to be a term called bubble jet printer. So, bubble jet printers in some way are thermal inkjet printers, where a bubble is created by heating. But obviously, you have a control when to create a bubble. If you pass the current, then there is a heater which will get heated. If you do not pass, then it will not do that. So, that control is with you. How much energy you generate, how much time you pass the current will also determine. So, resistance which is like a heater. So, you can do that. So, very interesting technology is this. The bubble generates very quickly, and so you can appreciate the temperature of the ink within the small chamber that we are talking about does not change much, because if temperature of the whole ink changes, the viscosity will drop and you will not know what to do. It does not happen, because most of the inks are aqueous based inks, it could be any solvent for that matter. So, localized wherever there is a heating, for example, there is a heater here, it gets heated, and just around this point the temperature rises very quickly. Say quickly means in fraction of seconds you are at somewhere around 300. That means water obviously has got converted to steam and bubble is formed, and based on the size of the bubble, which would depend on how much time the current was passed and the temperature was achieved, same amount of drop or similar drop size may get ejected. Interestingly, the pressures as high as so much, you can understand what we are talking about, but it is a very small area, very small volume. The moment the pulse is off, there is no current passing, the drop has also been ejected, the rest of the thing is quite cool, the steam gets converted to water, condenses immediately, there is no bubble. So, there is bubble created, bubble is finished. So, bubble does not go anywhere. Interesting. Now, these type of heaters which are very quick heating, very sensitive to things, are used in many devices. For example, your DSC, the small cell is there where you have a polymer on a crucible, you put it on top of a heater and efficiency is very high, and so it immediately gets heated, but locally the total amount of energy is low. But still what is happening is around that point there is heating, then there is cooling and heating and cooling and heating and cooling. So, this type of an arrangement is called a top shooter, that the heater is fixed on the top of the chamber, and so bubble is generated below that, and obviously it is being pushed. The same arrangement can be done the other way. For various reasons, people may say, well, it is easier for us to have a side shooter, but it can still form the drops in the same vans. So, once you know that there is a process available, then you can keep making designs which may suit your requirement. So, suspended heaters are also there. A suspended means that it is both sides the ink is there, and so you apply a field and suddenly there will be bubbles and one can get the same effect. So, here what are we controlling? Again there is only voltage control, but it is interesting that you do not need a displacement transducer. So, it is a concept slightly different, but it is also some companies are using thermal inkjet, it is called a thermal inkjet printing. The other one is called the piezo based system, but both are being used. One can have double shooters also, either at the top or at the bottom. So, the bubble size can be controlled because your area of the heating element may be different. If you need more volume, both of them may operate. If you need less volume, only one of them may operate. So, you have another control which can work on which kind on the control the size of the droplet. There were also some of the companies have used the same concept, but there is a deflection plate So, basically because this is a movable component, but obviously it has some amount of rigidity of its own. So, in some way you can control the size of the bubble and how much is going to get generated. So, the pressure control or the control with the force is going to be, pressure is going to be transmitted from one point to the other, instead of it going and striking the other wall. First the wave, you stopped it here, and so it goes towards the nozzle. So, nozzle could be interestingly placed at a point where with less of work ink gets deflected, ejected through that hole. It may be center or it could be side. So, that is way. So, what you say is once you know a technology exists and you can generate a bubble and therefore a ink, you can place these things anywhere and keep doing your job. Other technology which also has been used to create drops is acoustic excitation. So, you create, instead of a bubble creating the wave, pressure wave, you have the sensors which can generate ultrasonic waves, and so the pressure can be put on the top of liquid surface, and then this can come. It does not matter that all the technologies that have been pushed or all the possibilities that have been shown will be utilized, not necessarily. People will use whatever is good, and whatever is good means that you got to put large number of nozzles, large number of chambers, and within a small volume. So, the size of each one of them is so small that fabrication itself is a challenge. This is not like what so much large diagram that are made, but actually is very small. And if you want X number of nozzles in one area, let us say which can be more than 200, then you are looking, all of them have to be placed in that, and nozzle, because should generate a drop when required. So, that means so many chambers are also there, and everyone has to be controlled. So, everything is complex now. So, thermal drop on demand, if we summarize, is similar to piezo. Many principles are there which have been experimented with to help the jetting of the ink, like suspended heaters, multiple heaters. We have seen 2 heaters, but could be multiple heaters, and one can work. So, the bottom line also is that once a principle is understood, many possible combinations can be employed to increase the efficacy of the final product, which is a printer head. So, our product is a printer head. So, that head moves from one direction to the other. So, how many such small nozzle cum chambers can you generate, fix in one head? It is a challenge always. Some of the technologies sometimes are used because the other possible technology and the combination has been patented. So, once somebody has patented, you cannot use it. So, the only thing that can happen is that you generate something which is different than and not covered in the patent, and may not really have too much of an advantage, but it is different, and therefore, you can make a machine, make a sensor. So, till now what we have also learnt is that drop on demand inkjet technology uses either generally piezo electric transducers or thermal excitation based transducers. These are 2 major, others are available, but may not be used to such an extent. So, let us be looking at a piezo, size of a sensor. We said in the beginning that the displacement is very small. So, for generating something like a 30 picoliter of a drop size volume, area of the sensor in the firing chamber is approximately 30,000 micrometer square, assuming that the maximum displacement is 0.1 micrometer for one pulse, that is the maximum. So, if you generate, you want to get a 30 picoliters of a drop, you should have close to the area which is 30,000 micrometer square. Thermal printers require much less area. On an average, they could be 1300 to 1200 micrometer square. That means a smaller size. And if the element, which is the resistor, which gets heated, does not get corroded very easily, this will be the cheapest way to make inkjet printer. So, the piezo sensor also means that more compact packing of nozzles have to be done. How much compact you can make the nozzles? That is the part of a design which always has a challenge of something or the other. Solvent inks, pigment based inks, phase change inks, the piezoelectric, piezo inkjet heads are considered better and also considered more versatile. So, obviously, you can appreciate that the area of the sensor is not going to be changed every time you design a sensor, the area will remain the same. The only thing you can say is either you fire or you do not fire, or you control the voltage. If you can control the voltage, the total displacement can be considered. So, there is some advantage of piezo also, and therefore, drop volume control can be done by relatively easily, because the dimensional change of a piezo is fixed based on the voltage that you supply. On the other, fabrication of thermal jets is easy and less complex, and so people, you may get a large number of thermal jets also, but there are issues. Air dissolved in a ink. So, one is there is water which becomes steam, but you may also have dissolved air which can cause some problems. If you pour any liquid in any container, you see on the side, you see some bubbles, right? It is, unless it is very, you can see. So, corners, asperities, irregularities can create some air bubbles also, and they can be somewhere else also, not necessarily where you are interested. And what it means is that they can absorb the created pressure. So, you have created a certain amount of volume and you expected a certain amount of pressure to be created, so that a certain volume of ink could be ejected. If there are in the corners and somewhere else pressure absorbing systems, so air can be compressed. So, your total pressure which is available at the point of ejection at the nozzle can get reduced, and so there can be issue, but because of these things some control may be less. So, you are hoping that the control will be so much, but it may get less or more, depending upon how much the air was dissolved or was trapped, cleaned, not cleaned. Those type of things will come, and with time they will keep absorbing. So, these are some of the interesting things. So, it looks thermal inkjet may be better, but everything cannot be done by them. For example, these days the pigment based inks, after a lot of research, the binder is added in the ink. Now, you say, well, because binder can cause problems and choking in the nozzles, but nice binders are available. The question somebody can ask is, why can't we do a pre-treatment with a binder and print? But then where do you do the pre-treatment? The binder should be there exactly where the color is. You do not want the binder everywhere else. Then the binder cannot be washed away, because when you fix, it gets fixed. That is what is supposed to do the binder, it is supposed to make a film. So, it is not like a reactive dye where you have pre-padded with some alkaline solution. After printing, you can wash, the alkali will get washed from the areas where there was no dye. Wherever there is, alkali can get washed. But if you, there is no other way actually of doing a pigment based inkjet printing without adding a binder. So, if you have a thermal inkjet, and you have binders also, then choking can take place. They may polymerize during this bubble formation, and heater viscosity may change, and you can appreciate if there is a choking of these type of printer heads, you have to replace them. You will not be able to clean them, and which is obviously not cheap, because it comes all along with the circuitry. This is not something that you replace one chamber which appear to be blocked. Let me just remove. There may be just one single plate, there are nozzles, on top of them there may be chambers, and so it is a complex design. So, for pigment based inks, piezo based sensor will obviously be preferred, which do not do any heating. Robustness, life of an ejector, thermal inkjet can cause failure due to the ink related deposits on the heater surface. Reducing the conductivity, that is the heat generated is being blocked by something which has been deposited on the surface of the heater. Because heating, we have seen, have you seen those immersion heaters? When you boil anything, you see surfaces are obviously something gets deposited. Once it gets deposited, obviously the conductivity from the heater to the outside is not the same, and this depends only on that. And so, that would be interesting. One of the corrosion can take place, and the bubble formation and collapse is a violent process, and therefore, the life may not be so high. It is simple to design, less complex to design, but may be less robust. While the piezo based system is more robust and relatively easily controllable. So, there is some comparison, but you have companies today using both technologies and trying to make their things better, and one of them will be cost competitiveness. So, if you have to require a change, does not matter, it will cost the same. 2 of this will be equal to 1 of that, do not worry. So, that type of a thing people will do, but we must appreciate that both of them are difficult options. So, I think we will stop here and pick up next time.